Hello dear children, Mrs. Naziya Ustad from St. Joseph's High School welcomes you to the second part of the chapter Friction. In this video, we are going to learn friction, a necessary evil, and types of friction. Let's recall some of the experiences from our day-to-day life. We can easily hold an earthen pot, but it is difficult to hold a glass tumbler and it is likely to slip. Further, it becomes more difficult to hold a greasy glass tumbler. Similarly, it is not at all easy to move on wet, muddy track due to its smooth surface. You must have also experienced that you slip when you accidentally step on a banana peel. This happens because the friction is less when the surface is smooth. Thus, from these experiences, we understand that friction is necessary to hold an object as well as to walk. Now let us recall some more situations where friction is useful. Your teacher is able to write with chalk on green board only due to friction between the chalk and the board. Also, we can ride the vehicles on the road because of the friction between the surface of the road and tires of the vehicles. Without friction, you cannot fix a nail or tie a knot. Thus, friction is useful in many ways. But sometimes friction is an evil that is not useful. For example, it wears out the materials like screws, ball bearings, or soles of shoes. In some cases, friction can produce heat. The simplest example is when you rub our palms together for a few minutes, they become warm. You must have also experienced that jar of a mixer becomes warm when it is run for a few minutes. Similarly, when a machine is operated, heat is generated, which causes wastage of energy. In such cases, we need to minimize friction. Thus, we learned that as there are two sides of a coin, friction is useful in some cases, whereas it is not beneficial in others. Consider a stationary sofa which you want to move in your living room, and this sofa is really heavy. What happens when you give it an initial push? Yes, you're right, nothing happens. The sofa doesn't move even though you are applying a lot of force. Why do you think that the sofa doesn't move? Well, the answer is static friction. The force that you applied is balanced by the frictional force by the floor, and the force is applied opposite to the direction of your push. This force is nothing but a static friction. The concept of static friction is really amazing. Why do I say that? The reason for why do I say that is because this is a self-adjusting force. As you increase your force of push, the force of static friction increases too, and the forces are still balanced. Now I know what you might be thinking. So after a few seconds, the sofa begins to move, right? What happens to this static friction then? Let's discuss with the help of a simple graph. We assume that the force applied is horizontal force represented by x-axis, and the frictional force applied by the floor is represented by y-axis. Now, as you increase the horizontal force applied, the frictional force is also increasing accordingly to keep the sofa at rest. This continues till a point when the sofa just starts moving, and that's where the static friction ends and the sliding friction begins. The sliding friction is more or less constant if you notice. This part of the graph is static friction. It's when the sofa is not moving in spite of force you are applying, and this part of the graph is a sliding friction when the sofa begins to move. The point around which the sofa just begins to move is called the breaking point. Is there anything else you noticed in the graph? Why is this line at lower level than the maximum static frictional force? The reason is simple. If you have ever pushed a sofa or some heavy object on the floor, you would have realized that pushing it is little easier when it is in motion. Yes, it's because the sliding friction is lesser than the static friction that is offered by the floor. That was the concept of static friction for you. So we have seen 3 types of friction so far: static friction, sliding friction and rolling friction. Can you place them in the increasing order of their force being applied by each? Yes, static friction is more than the sliding friction, which will be more than the rolling friction. Let's say you have this cuboid shaped box placed on the table. Try pushing it a little. You will require some force to push it forward. Now place this same box on the top of a cylindrical shaped pencils and push it. What do you notice? You will notice that the force required by you to push it to the same point as before will be lesser. Why is that? Do the pencils reduce the friction between the box and the table? Absolutely. But it's not about the pencils. It's about the shape of the pencils. They are cylindrical. Assume you are traveling to another city and you are carrying luggage weighing around 25 kgs. If you are unable to carry the bag, the only option you have is to drag it on the floor. But you will still require a lot of effort to drag your bag. But what if your bag has wheels under it? Won't it be far easier to carry it around? Yes, it will be easier. But the question is, why? Why is it easier to roll a box over cylindrical pencils relative to pushing it on a flat surface? Why is it easier to carry the bag around when it has rollers under it? Hold on to this thought. I'll come back to it. Before we discussed the above situations, we need to understand what sliding friction is. The concept is simple. It is the frictional force which opposes the relative sliding motion between the two surfaces in contact. What does this mean in simple words? It simply means that if an object is in motion on a surface, the frictional force that is offered by the surface is called the sliding friction. The keywords here are sliding motion. The two surfaces have to be in relative motion with each other. In our example, when a box is moving on the table, we say that the box is in relative motion with the table. The resistive force applied by the table when the box is moving is called the sliding friction. Remember, the object has to be in relative motion. Because there is moment involved, this force is also called kinetic friction. Now consider the example of the luggage in which we don't have the wheels under it. When we move the luggage, what will the relative force applied by the ground called? Yes, sliding friction. But what happens when we attach circular wheels at the bottom of the luggage? Yes, the friction gets reduced to a great extent. This type of friction which arises when an object is rolled on a surface is called rolling friction. It is a force associated with rotational moment. Now can you tell me by pure intuition about which force will be lesser? Sliding friction or rolling friction? Yes, rolling friction is usually lesser than the one associated with sliding friction, and that's why attaching wheels at the bottom makes it easier to move the object around. And similarly, moving the box on the top of the cylindrical pencils is also easier. Can you think of some more examples where the concept of rolling friction is used to reduce the friction? Yes, tires of your car. When the car is in motion, the ground applies a force of resistance which is nothing but the rolling friction on the tires. Do you remember seeing ball bearings? They are spherical metal balls used in many mechanical structures which have moving parts. They are generally made up of stainless steel, brass or ceramic. They reduce friction to a great extent, which in turn reduces the wear and tear of machines' parts. Dear children, here I would like to conclude this video, and further concepts will be learnt in the next video.